here's a summary of what we'll be covering in this project today. We'll start with a brief introduction to the inverse design method. Then we'll be looking at how the chiller cycle analysis and mean line design of a centrifugal compressor stage can be performed simultaneously. Then we'll see how the impeller can be designed using the 3D inverse design approach. We'll also briefly look at the design of the volute, and then we'll evaluate the performance of the compressor stage based on a CFD analysis. And finally, we'll wrap up with some concluding remarks. So the awareness in energy saving has continuously increased in the past decades, and this has led to higher energy efficiency requirement on HVAC applications. And in the refrigeration and heat pump sectors, continuous efforts have been made to reduce the energy consumption to meet the new standards and regulations. And of course, the performance of the compressor is crucial to the vapor compression system efficiency and operation. And here, compared to reciprocating and screw compressors, centrifugal compressor has the advantage of high operational efficiency at full load and relatively compact size. It also enables the usage of oil-free gas lubricated bearings, which doesn't have oil lubricant, impairing the heat transfer efficiency of the heat exchanger. And so the system efficiency can be boosted to a higher level. And finally, centrifugal compressor also supports a wide range of capacities. But a major challenge is the part load performance, and because a chiller can operate at less than peak load for more than 90% of the time, efficiency and stability at part load operation is very important to minimize the overall energy cost. And since with the help of variable frequency drive, centrifugal machines can operate at very low load conditions, and so the efficiency at part load condition is still a key area to be improved. So let's start with an introduction to the idea behind the inverse design approach, which we use throughout this project. And as you can see in this workflow, these are the inputs that are used by the inverse design method to give us the final blade design. So apart from some basic parameters, these blade loading inputs are really flow related. And so once you have a good understanding of your specific flow issue, whether it's profile loss, secondary flow, or shocks that you are dealing with, it's possible to come up with guidelines on the optimum blade loading to tackle each of these issues. And actually this know-how has generality, which makes it suitable for all your compressor applications. And so what's interesting then is that you only need to rely on your knowledge of flow physics, and then this method will work for you regardless of your compressor size or which specific speed regime it falls under. So this makes the entire process very intuitive and removes any empiricism that's commonly seen in conventional design methods. Now let's look at the design of compressors in a bit more detail. So across the specific speed range, compressors are subject to various flow phenomena and loss mechanisms which are dominant in that particular range. For example, as you can see in this specific speed chart, leakage and secondary flow effects are more dominant in the lower ranges, whereas shocks, profile losses, and corner separation in vane diffusers take priority in the higher ranges. And in fact, with inverse design, it's possible to come up with a set of optimal guidelines based on these fluid dynamic considerations of reducing the dominant flow losses for your compressor. And this is actually what we aim to explore through this project.